How many people want to change the date of the exam?
Huh?
Move it to next week on Wednesday, before
Wednesday.
the
Not
holiday.
next week, Wednesday.
What's that?
Wednesday originally.
The 26th, Wednesday.
What day do you want the exam?
The 26th.
26. November 26.
Mhm.
Wait, November 26th is the exam?
Yes.
I don't know. I want to know.
That's the Monday.
Yeah, 26 is good.
Now 26 is moving it back rather than moving it
Oh, we wanna move it up?
forward.
We don't want to move forward.
No, we
No,
wanna move
no,
it
no.
up.
He
Forward.
No, they want last class on Monday, 26.
Does November 24 follow the holiday?
No, November 26th is right before the holiday.
26 is the last Wednesday, and then we have
Oh,
the same
26 is the last Wednesday?
And then we have the holiday.
Okay. Let me go like this. I see, we have the holiday here, and then we have this week here.
Yeah.
Next week is finals.
All right. Everybody's in agreement to make it the 26th?
Yeah.
Yes.
Yes.
Is
How
there
many
like-
no's?
What's the disadvantage? It sounds good to me.
What happened?
We're going to move the exam to the 26th.
Oh, dang. Alright, I guess I can be okay with it. I mean, gosh. I had yoga class that day too.
All right, okay.
What did I miss?
I'll change that. I'll move that back. All right, so, last time I wasn't very satisfied with what we came up with for the solution. Maybe dim the lights in the back, unless this is okay, I don't know.
That's fine.
Not too, right? I wasn't very happy with this solution. The problem is this is exercise 4. It's in this functions, L4 functions. And exercise 4 was to, oh no, that's not right, not functions. It's in arrays, L6. To implement a function that does vector insertion. So give me a vector that contains a sorted sequence of integers. And a sequence of integers in an increasing or non-decreasing sequence. And then also the function takes a value k, an integer k. So given that the function gets this sorted vector plus a value k, put k in the right spot in the vector to preserve its sorted state. And we looked at some examples and kind of banged out this algorithm, but it's, this is one solution. There's this one solution, but I thought I would go over this again and try to come up with a better solution, a slightly better solution. So look, here's an example. Here's a vector with 4 values, 3, 6, 7, and 12. And we want to insert the value 8 in there. So obviously it goes before the 12 and after the 7. So how can we think about that? Well, we can append a 0. We need an extra slot in the vector, so we need to push back something. And then we'll set the index in our loop. So we'll need to use a loop because we don't know how long the vector is. So it could be 1,000,000. We're going to start at the end. And we're going to copy values back until we find the right slot to put this value k into. And so what we can do, this the key is to understanding this algorithm is to understand what I represents in the code. And here, the way I think of I is that I is the location that we are considering for k. Do we put k in I? If I is not a good spot for k, Because basically, then if I is not a good spot for k, then decrement I and consider the next spot. But also, each time we do that, we copy over the value that's at I minus 1. So if we look at position I, we say, all right, I here, we're going to start the algorithm here. The I is at the end of the vector. Is this location, which is location 4, the vector of size 5, is this location, position 4, a good spot for k? Well, to know that, we have to look at the value at I minus 1. So when we look at the value at I minus 1, we see a 12. But what we have coming into the function is an 8. And so we don't want to put 8 in position 4 because it would be smaller than the value before it. So it would no longer be in an increasing sequence of values. So we copy over this 12 into the last slot here, into position 4, and we decrement I, and then we start all over again. Is this position, position 3, a good position for the value 8? Well, the way, we already know that the 8 is less than the 1 that's behind us, because we put the thing there. We already compared it to that one. So what we do is we do the same thing. We compare the value 8 to the value at I minus 1. 8 is bigger than the value, or equal to the value at I minus 1. And so this location for I is a good spot for the 8. So we write it in there. So let's see what we have here. We push back the 0. We start with I equaling v dot size minus 1. And we continue while I is greater than 0. Actually, I think I'm going to try using a while loop this time. Let's do it with a while loop. So this is v dot size minus 1. And then while I is greater than 0. Actually, it's not much of a difference, is it? Now that I think about it, I think I'm going to back out of that. I'm going to stick with the for loop. Okay, so here I starts at the end of the vector, and it continues until it hits this position 1, and it executes the code for that. But then when I is set to position 0, then we don't continue with the loop anymore.
Would the condition be I is greater than or equal to 1?
Yeah, we could do it like that. Actually, I want to do the while loop again. I'm trying to get it to look, just nice. Let me try the while loop again. So we could do greater than or equal to 1. It's the same thing. Strictly greater than 0 is the same thing as greater than or equal to 1.
Yeah, it is.
Yeah, actually, I keep changing my mind all the time. I'm going to change it again. All right, here we go. So we've got an I. Remember, here I is the. We'll put a comment in there. Is I a good location for k? That's the question. If it is, then we write k into that. Then we're done. No, then we write k into that location. Then we do this. If it's true, and so there's going to be some condition. If the condition is true, if I is a good location for k, then we write it in there. Else, if, and I'm going to do this because it's hard for me to explain this. Else, if I is 1, if I is not a good location for K, but I is 1, then we know that that K should go into position 0. That's what I think. So if I is a good location for K, then let's store K at I. And then otherwise, I think we can do this as well. Otherwise, if I is 1, then K must go in the first position. Otherwise, we have to move the value at I minus 1 to slot I. Every time I do this, I come up with a different solution. In lab, I had 2 other solutions, but this is just to show you that there's many ways of solving the problem. Of course, now the question is, what about this condition? How do we express the condition that I is a good location for K? Well, if K is greater than or equal to, what was that? You want to say? I'll go with what you want.
Oh no, I was gonna add two conditions in there.
Add a condition?
Add 2 conditions in there.
No, we only
Add
need one condition
one
here.
condition.
So I'd say if K is greater than or equal to V of I minus 1. If K is greater than the value before I or equal to the value before I, then let's put K in I. And of course we're done. If I is not a good location for K, then we're going to want to, move the value at I minus 1 into I in general. And then we'll decrement I up here and start all over again. But we need to have this, this check here. If I hits 1, then we don't want to, after we decrement I, we won't have any, we'll be at slot 0, we won't be able to compare I to, we won't be able to compare K to anything before slot 0, so that we know that K must go into slot 0. Anyway, what do you think? Let's check to see if it passes the test. It does not. It's the problem. Assertion failed V of 1 equals 4. That's in line 60.
See, what's the second vector?
What's that? Oh,
The second one, yeah.
the test code is incorrect. The test code is not right.
Try
Okay.
it again.
Same thing. Did I save it? This should be, so U has values 4 and 7. We want to insert 1. So it should look like this. What's the problem there? Maybe because we have to do this. See, the problem is we didn't, when we put K in V of 0, we need to copy V of 0 to V of 1. I'm sorry, that's VF0. We didn't move that. Coming up with a terrible solution this year. It's like usually this is a really easy problem to get, but this is just messy looking to me, but I think that's going to work now. So that's one way to do it. What about this test case here? When k is 30, it should go on the end of the vector. So this should, let's look at this test case, 6 and 9 and inserting 30. The result should be 6, 9, 30 like that. Let's see if that case works as well as these others. Was it 3 and 6? Anyway, it doesn't matter. It needs to go into the last slot. So if we have a vector with 2 elements, 3 and 6, and we insert 30, it should go into the last slot. The other values should remain unchanged. Let's see if that works. Ah, that one might fail. It works. Why does that work?
Hard drive?
Huh?
Bad hard drive?
Here, what do? We just take v of I. So v of I is 2. So we write 30 into slot 2, and then we return. So we're done. All right. Any questions about this one? You can get this code to be more compact. Actually, I'm not going to do that now, though. All right. Let's move on. Let's look at binary search. All right, binary search is a basic algorithm that lets you locate the value inside an ordered sequence. So, for instance, like a telephone book, you want to look for a name in a telephone book. Say, like Gomez. Right, you take the book and you open it in the middle, and you see, Montgomery is there. So, oh, Gomez is to the left. So you discard the second half of the telephone book, and you split the left half again, and you keep splitting in half, and until you find the page that has the name on it that you want. That's called binary search. And so. In programming, we have an ordered sequence of values. So in this case, we're going to use a vector of int. And in this problem, it asks for a function that returns true or false whether the value k is in V. So determine whether k is in V. Return true if it's in V, return false if it's not in V. But don't do it in the slow way, like, is Gomez in the telephone book? Well, I'll use binary search to find Gomez in the telephone book. I won't look at page 1 and say it's not there, page 2, it's not there. That's called a linear search. So a linear search is very slow, and a binary search is much faster. So I want you to use a binary search to solve this problem. Was there a linear search problem in the assignment? I think there was.
Yes.
Yeah.
Number 3.
All right, so this is an improvement over that. And this is lab 7, right? Okay.
Yes.
just get a basic, sorry. So here's the function we need to implement. Let's create a test case for it. So we create a vector of int called v. And let's push back some values. Needs to be in order, so I'll push back, say, a 3 here. Maybe I don't want that many. So 3, 5, 7, 9, like that. That's 4, maybe 5. And then we'll have an assertion. We'll assert, if we call the insert binary search function, pass in v, and pass in a, say a 5, should be true. 5 is in v. So we assert that when we call binary search with v and 5, it returns true. But what about 6? 6 is false. So we can do a lot more tests. We'll just start with those. All right. So we need some variables. First thing we're going to have, we'll have a start index, call it 0. So it's just like that, the vector. We're going, the area, we're not sure where it is. It could be between 0 and v dot size minus 1. So we'll call the end of the vector v. That'll be v dot size minus 1. So if k is in the vector, it has an index that's somewhere between and including s and e. All right. Then there's another value called m for midpoint. Actually, I'll do that in the loop. So we're going to have some loop here, some condition. We're going to repeat an operation over and over again. We don't know how many times we're going to need to split the vector. We're not going to know how many times to move s or e towards each other. So what we're going to do is, like s and e are like bookends, and we're going to move them towards each other. We're going to narrow in on a single location. And if it's not at that single location, we didn't find it. Or if we find it during the narrowing process, if we find k, we're done at that point, return true. So we're going to go through steps where we move, either we move s to a higher value, or we're going to move e to a smaller value. We're going to squeeze s and e together, trying to find k. And if we squeeze it all the way down to a single slot and still don't find it there, then we know it's not in the vector. So we're going to, the condition will be something like this. Continue while the start value is less than the end value. And it might be less than or equal to, I'm not sure. And maybe we'll do that. Not sure yet, to think about it. So we're not going to look at position S or position E. We're going to look at the midpoint between S and E. So we need to calculate the midpoint. What's the midpoint between S and E? What's the formula? Everybody know? It's not S minus E. Huh?
Isn't it S plus E divided by 2?
S plus E divided by 2. So it's the average of S and E. The average of S and E is the midpoint. So you were close. Yeah. Huh? So here we're going to do S plus E divided by 2. Now, if we get, if S plus E is an odd number, we're going to get truncation. So if S plus E were to be something like a 5 divided by 2 is 2.5. Well, we're storing it in an int, so we truncate. So m becomes 2. Because we can't use floating point values. These are indices in a vector. They have to be integers. So you can't split a vector. There's no exact, a midpoint, only odd numbered vectors have a value at a midpoint index exactly. All right. So once we compute m, then what we want to do is compare the value at m with k. Well, I'm going to do it like this. If v of m, if k is bigger than v of m, what do? So the value k, we're looking for k, trying to find k in a vector, but it's bigger than the value at v of m. That means we can move s up to the midpoint plus 1. See, that's how we move. K is big. It's bigger than the midpoint. So let's bring S up to the midpoint. But, we don't need to put S on the midpoint because we just compared K with the midpoint value. So let's bring S all the way up to the one past the midpoint because we haven't looked at m plus 1 yet. Else, what if v of m was greater than k? I don't like the way, I don't like the order that I'm doing this because it's not how I read it. If k is greater than v of m, it's the same thing, I'm just moving it around. And then here is if k is less than v of m, that's how I think it. So I'm going to modify my code to get closer to how I think about the problem. So if k is less than the value at the midpoint, that means k is small, so we're going to bring the end index down. So we're going to let n equal m. But wait a minute, we looked at v of m. So we don't need to look at v of m again. So let's subtract 1 from there. We look at we'll bring e down to just 1 under m. I forgot this parenthesis. Else, we have the case that v of k, k, equals v of m here. If these two conditions are false, this one here, if it's not the case that k is greater than v of m, and not the case that k is less than v of m, then it has to be the case that v equals v of m. What do we do then? Turn true. Very good. And if we go through this loop and we hit this condition to say, hey, we can't look at numbers anymore, we've looked at everything, and we exit the while loop, what do we do here? Exactly, turned false. We didn't find it. We squeezed S and E together as far as we could. We didn't find K in there.
Why do you have K is equal to V of M commented out?
Because it has to be the case. What we could do is like this, watch.
Oh, okay. Inserted in the
We can put an assertion in there. Because look here, K is not, the only way we get to this code here is if K is not greater than V of M and K is not less than V of M, K has to equal V of M. So we don't need to spend the CPU time testing a condition that we already know is true. But just in case we didn't get the logic right, we can put an assertion in there, take it out later. Yeah.
Would it be more efficient to look and see if they match as like the first step? Because then
Well, if K appears frequently in the vector, that's probably faster. But if K doesn't appear frequently in the vector, I think this is more efficient. That's a good question. They're all good questions. All right, so but I'm still not set yet. Should it be S less than or equal to E, or should it be S strictly less than E? If S and E equal each other, let's suppose that S and E equal each other. I think it's that. Maybe I'm wrong.
Then K would equal V of M.
Huh?
Then K would equal V of M.
See, here, when we modify S, let's suppose we modify S, and S and E become equal at that point. Let's suppose we look here. If K is greater, I think we can omit that. If we modify S and S becomes E here, then K can't be at S. Is that right? Okay, no, I think maybe it can. I better put it in there. Let's check. Let's see how this works.
You know it's not going to compile, right?
What do I need to fix?
Insert vector, or the include vector, and at the bottom where you have the assert for true and false, instead of the ending of the code, you have
Wait. Which?
at the very top, include vectors.
Which line?
Line 3, you got to include vectors.
or it's just
Oh,
like-
yeah, thank you.
And then on line, scroll down. Line 32 and 33, you didn't close the code. You actually put parentheses.
Thanks. Good job.
Get rid of that set though.
Get rid of.
On the right side, get
Yeah.
rid of that extra ones. There you go.
Great. Good job. Thank you.
That's Visual Studios, yeah.
Yeah.
It's like tell your professor, I'm like, all right, calm down.
All right, let's go here.
The vector.
Let's compile and run. All test pass. But our test code is not very good.
Is it good enough for a B?
Yeah, this is good enough for a B. Let's get an A. Let's check a value that's smaller than the first one. That's false. Equal to the first one. And equal to the second one. So we're equal to 5. Let's see if it can find 5. It can find 7. It can find 9. and it should be able to find 12. But it should not find 6. It should not find 4. It finds 7. It should not find 8. Finds 9. Should not find 10. It finds 12, but it does not find 13. Let's see if it works now. So basically checked kind of every spot in this vector of 5 elements. Looks good. The other thing we could do here is see if it works correctly with 4 elements. We'll just keep the same vector. We'll just call popback. That removes the last element, element 12. And then we'll go through this same thing again. So now the vector is goes up to 9. So 12 should no longer be in there. I'll just leave the other ones in there. Looks good. So it works with a vector with even values, even number of values in it, and a vector with odd number of values.
So what is a popback, you said?
What's that?
What is a popback?
Popback means remove the last element, remove 12.
Oh.
Popback means remove the last element. Okay. See here, after we push these on, the size of the vector is 5. So put an assertion in there. After we call popback, the size of the vector is no longer 5, it's now 4. Okay? And it's the last element that was removed. We could put an assertion in for that as well, but the test code verifies that. No. Okay. I think that's the best explanation of binary search I've ever given. But that insert problem, that was my worst explanation I've ever given.
You know it? So you're good, right?
All right.
You would like to volunteer for the next one.
Oh, great.
Here you go. Example 2. Because you know it, right?
How about this finding the maximum value in a 2D array? What is this stuff anyway? This lab is binary search. Finding the maximum value in a 2D array.
He said it's easy. Let him do it.
This one is easy, yeah. Oh, here's a linear search. So do the same thing, but don't. Here, in this case, why would we want to use linear search if we could use binary search?
Mix things up.
Actually, we can't use binary search because they're not in. Here, the sequence of values would not be in order, so we're forced to use a linear search.
Search one by one.
Yeah. And guess the number game. So all of these you need to do. What do you want to look at now? Basically, you need to do this this lab 7 with all those problems, and then prepare for this exam 3. which will cover the material up to lab 7. So on exam 3, I will ask for binary search on that exam. Absolutely, 100% guaranteed. So I had to write out the algorithm for binary search.
What's number 8?
We can finish now unless you want to look at a lab exercise. I can show you how to do it if you want.
Can you do lab exercise number 2 through 5, please? Just, FYI.
Which one? What do you want to see? Anybody stuck on something?
I'm stuck
Lab
on.
6,
What?
the lab 6, those,
Lab 6?
yeah.
Which one in lab 6?
Oh, she means from lab 6. Which exercise?
That number 8,
Unlucky vectors.
unlike it.
Yeah, I think I always ask something about lucky and unlucky vectors on the exams. So you're going to get one of these, I'm sure. So let's do this one.
Oh, yeah, let's go talk to Monica too.
Oh, let's go talk to Monica. Professor, we're gonna bounce out. Well, say didn't give me the answer, so I'm good.
Refer him to your notes.
All right, exercise 6.
Last 6 exercises.
I'm sorry, lab 6, exercise 8.
Take this.
See that?
So we need to implement this function isLucky. It takes a vector and it returns true or false. If the vector contains lucky numbers, we return true, otherwise return false. All right, if the number 13 appears in the function, if it appears at least once, then it's unlucky, and we would return true. Write test code that tests every statement in the function. Use assertions. All right. So we'll create a test here, V, and let's do this. Pushback 4. So is V unlucky? It's false. V is this function, this vector. There we go. So we have a vector with a single value in it, 4. And when we pass that to the function, it should return false. Actually, let's create a better example. See, that's -4, maybe that's 100, something like that. Let's put a 13 in there. Now it's unlucky. Let's push some more values on there and make sure that it still comes back as unlucky. Let's put a bunch in there. Does the test code look all right? Now, in the problem, and I state this, write test code that tests every statement in the function. And that's why I'm testing that testing when the function returns false and true. So if we test for both of those return values, we'll end up executing every statement in the function. Anyway, the function that I envision here. So let's, the vector is not in a sorted order. The values can be in any order. So we'll need to do a linear search. So we'll start at position 0, and we'll continue until we get to the end of the vector. So what do we test for? We're looking for the value 13. So if e of I is 13, return true. It's unlucky. When do we return false?
It is not,
When it's not 13.
it is not 13.
When the first value is not 13?
No, when any value of the
When all values are not 13. When do we know that all values are not 13?
After the whole loop is run.
After the loop runs. Does that make sense? That's the mistake that everybody makes. They have an if-else in there. That means if you have if-else in there, if v of I is 13, return true, else return false. You're only going to look at the first value in the vector. There we go.
And how exactly did you set up the v dot pushback? Like what was kind of
Well, I just created a vector with 3 elements here that don't include 13.
okay?
Then I wanted to see that calling is lucky returns false. But that test code is incomplete because here I'm asking, I want every statement to be executed. And actually, this is a substatement, return true. So this is not being run. We're only testing the case that 13 is never found. So we're just returning false here. So we don't branch into this code right there. So I pushed back 13 here and then called the function a second time, and now it returns true because there's a 13 in it now. But I wanted to make sure that it still works even if 13 is not the last element, because this is testing a boundary case that 13 appears in the last location. So I just added a few elements to make the vector look more like a typical case where 13 appears somewhere on the inside of the vector, and then test that it still returns true.
So less than 13 is returning true.
Huh?
Less than 13 is returning true, right? It says true. It's not lucky.
If every value is less than 13, it returns true. Well, you can have values that are bigger than 13. That's okay. We only return true, so it returns false. If everything is less than 13, we return false, right? We only return true if we find a value that exactly equals 13. And if we don't find a value that exactly equals 13, we return false at the end after checking all values. Any others? I think we looked at flatten. Did we do flatten?
No.
Do you want to do flatten?
Yes.
Oh. All right, let's look at flatten. That is 10. So we're getting a are you sure we didn't do this?
No.
Oh, okay.
7, 8, 9, and 10 we haven't
All
realized
right.
yet before today.
Okay, let's do this here. So flatten, we pass in an array that's 100 by 200. So we'll need we need to create that array. So we'll take integer, I can't remember how to do this. So it's an array of int. Did I get the syntax right? I think that's it. We need to return a value here. A vector of int, we call it v. We'll do stuff, and then we return v. Now it should compile. So we're passed in an array of values, and we flatten them out, put them in a single dimensional vector, and then we return that vector. But we need to do work in here. What is it that we do to flatten the vector? Well, let's create the test code first. So we define the array A. It's 100 by 200. And J ranges from 0 to 200. I ranges from 0 to 100. J ranges from 0 to 200. Put a value in there. Did I ask for test code here? You know what? I didn't ask for test code. And actually, I want to skip the test code. I'm not going to ask for test code for this in the exam. It's too much coding to do. So I'm just going to leave that out. Let's just implement the function. I'll show you how it works. How do we flatten this? Well, actually, we use this. So we get every value in A, and we simply push it back onto V. What goes here? And then we return V. Done. What do we push back? What goes in here? Anybody?
VI.
VI? No. We're taking the values from A and we're stringing them out across B. Huh? Someone's got to get this.
AIJ.
Huh?
AIJ.
AIJ, thank you. You know, it doesn't work that well for me to just show the problems all the time. I really should be working on these in lab. So, you know, maybe this is the last one I show you, but that's what it looks like. So, you know, J is ranging across the columns, I is ranging across the rows. And for each row, basically we push row 0, then we push row 1, and then we push the elements from row 2 and so on. And that's it. Then we return V. And we're going to, on this exercise, I'm going to omit the test code. I'm not going to get into that. So that would be the answer right there. Yeah, that's good. That's good enough. All right, that's enough for today. Any other questions?